Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on sodium integral effect test loop for safety simulation and assessment will be presented by Dr. Lee shortly. Doing the introduction today is Dr. Patricia Pavier. Dr. Pavier is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's also the National Technical Director of the Molten Salt Reactor Program, and she's the chair of the Gen 4 International Forum Education, Training, and Working Group. Patricia.
Thank you very much, Bertha. Good morning, good evening, everyone. It's a pleasure to have Dr. Ji-Won Lee with us today. He's currently the project manager of Stella program, and he's the team leader of the sodium experiments team in the Korea Atomic Energy Research Institute. He earned his PhD in nuclear engineering and established his career as a sodium experiment professional. He supported the technical director of the expert group, and now he's a member of the Gen 4 International Forum Sodium Fast Reactor System Steering Committee, Safety and Operation Project Management Board. His expertise is in the sodium heat transfer of both analytical and experimental works. He has experience on handling and managing the alkali metal and evaluating the performance of various heat transfer systems using various analysis tools. He has a deep understanding of the liquid metal system from component level to system level. His recent interest expands to the innovative instrumentation for high temperature liquid metal, as well as various liquid metal applications, such as the thermal energy storage system. So without any delay, I give you the floor, Dr. Lee. I really thank you again for volunteering to give this presentation. Thank you.
Thank you. Thank you for the warm welcome and introduction. Good morning, afternoon, and evening. I'm pleased to give a seminar on Stella program here in Gen 4. My name is Jae-Hwan Lee again, and I work for Kerry. Currently, I'm in charge of all the sodium experiment activities in Kerry, including Stella facility. I started my career with the Stella facility after PhD, and now I'm in charge of it. I'm very lucky to have this opportunity. I'm going to talk about Stella program, which is divided into two phases. Stella 1 is what we call it a separate effect test, and Stella 2 is an integral effect test. More detail, Stella 1 is a component test facility, whereas Stella 2 is a system test facility. So I will briefly tell you about how these facilities worked or how it is doing. And after that, I will share the future plan. So this is summarized overview of Stella, and actually it contains all the key information. Stella program was first launched in 2009. Of course, the discussion and debate were there before this time, but it started its first footstep with the funding in 2009. It is a large-scale sodium test program that Korea never had experienced. As a first step, Stella 1 facility to test key component was designed, constructed, and operated. During this period, the reference reactor was changed from Calimer 600 to PGSFR, and we added extra tests for new component to be consistent with PGSFR and which is SELFA. This is actually an extension of Stella 1. The reason we have different name is that the facility is physically separate from Stella 1, although it shares same purpose to support PGSFR. In year 2012, Stella 1 finished its construction and accomplished its primary objective in 2014. And then it was modified to test the extended range until 2017. In case of Selpha, it finished its construction in 2016, and the experiment was done at the end of 2017. In this phase 1, the focus of experiment was to test the thermohydraulic performance of key heat exchangers. And at the same time, there were many implicit activities that must be accompanied by. Dealing with such a large amount of sodium was a whole new experience for us. With the data here, we were able to validate the thermosizing design codes. In parallel to the Stella 1, Stella 2 was also ongoing. The design started in 2014, but the concept and higher level decision making was far earlier. The construction was finished in 2020, and since then it is actively in operation. The focus of phase 2 is to observe and investigate the system dynamic behavior. It's rather a comprehensive evaluation test of the system. In contrary to the phase 1, the result of this will be used to validate the system codes. So let me talk about the reference reactor first. As I told you earlier, the reference reactor was caliber 600 at the beginning of the program, but the reactor design was changed to PGSFR, and the Stella facilities are designed to support it. In this slide, some of the main design features are listed. On the right side picture, there are more in details, but I won't go into details because I'm sure that you have enough understanding as long as you are in this Gen 4 International Forum. Before I move on, just one thing that I have to mention is highlighted in blue here. In PGSFR, there are 4 independent decay heat removal systems. 2 are passively working and 2 are actively working. This is to satisfy the diversity and redundancy concept of safety. Can you go to the next slide, please? It isn't working now. Thank you. These are some illustration of PGSFR. If you need more information about PGSFR, there are plenty in open sources, or you can email me. So I just move on to the main words. Next slide, please. Okay, next slide, please. Separate effect test. So that's it for the appetizer. And let me move on to the main dish. As I told you before, Stella 1 is to test the heat exchanger, and they are DHX and AHX. DHX is a straight tube type sodium to sodium heat exchanger located inside the sodium pool. On the other hand, AHX is a helical tube type sodium to air heat exchanger. These 2 components are the key for the safe decay heat removal. So using almost 18 tons of sodium and about 2.5 megawatt power, these 2 components were tested. And you can see there's another item here. Since we have a large amount of sodium and facility, we also wanted to test the mechanical pump performance under sodium environment. We designed the pump, we tested in water, and finally, we tested in sodium to compare the result. Some of the details for Stella 1 is in this table. 18 tons of sodium, 600 degrees C, and 10 bars are the design values, and 2.5 megawatt in total power. And flow rate is max to 25 kilogram per second. It is not shown here, but the max flow rate to test the pump, the mechanical pump, is 125 kilogram per second. Next slide, please. And this is Selfa, an extension of Stella 1. Again, it is to test another key heat exchanger called FHX. FHX is a fin tube type sodium to air heat exchanger. As I told you before, there was only DHX and AHX in Caliber 600, but the reactor changed to PGSFR and the safety feature was enhanced with diversity mean. So, actively working heat exchanger was added. There were some people asking why we built a separate facility for this instead of just adding to Stella 1. Well, at that time, we had opportunity to reuse the existing structure and recycle some of the equipments. And so we saved the money. Simple reason. It took less budget to go this way. Some of the details for Cepha is in this table, just like the one you saw in previous slide. Comparably, the sodium amount is small and the power is small, but it just fits the purpose of this test. Next slide, please. The model heat exchanger for test was designed based on 3 requirements. We adopted volume scaling, and so the length scale is 1:1. We conserved the tube size, pitch, and heat transfer coefficient, and the delta T. As you can see in the table, for DHX and AHX in Stella 1, the area ratio is 2/5, and for FHX in Selfa, it's 1/8, 1/8. Next slide, please. There are 3 in-house codes for thermosizing of heat exchangers. The name is SAXA, AXA, and FAXA. They use control volume approach, solving the basic 3 equations. As you can see on the right side, the mass balance, momentum, and energy balance. Next slide, please. So this is summarized table for each code description. There are information of the most important part, the correlations for pressure drop and heat transfer. If it's too small to read, please refer to many open sources that we have published. Okay, next slide, please. Here are the summarized results of Stella 1. Basically, we set the inlet temperature of each heat exchanger for tube side and shell side, and we measure the outlet temperature. Then we can analyze the temperature as well as the heat transfer capacity. Since this data was used for licensing, all the experiments were under thorough QA procedure, and the evaluation was done with ASME uncertainty analysis guidance. Let's look at one by one. For sodium to sodium test, we were surprised of the excellence in deviation of experiment data from code calculation. As you can see here with numbers, this was really, really good. And for sodium to air test for helical tube, the sodium side was still very good, while the air side was comparably moderate. But in general, 10% is still a good result if you think of other air experiments. For sodium to air test for fin tube, discrepancy was in similar range with the helical-type experiment. Again, for more information, please refer to the published papers with these things. Next slide, please. And lastly, with Stella 1, we were able to test the natural circulation flow development. Because it is 3-loop system, we can set the condition for natural circulation to occur in the sodium loop. So there is one sodium loop for heater and DHX shell side, and there is another sodium loop for DHX tube side and AHX tube side, and there is one air loop for AHX shell side. That makes 3 closed loop, 2 closed loop and 1 open loop. With this experiment, we were able to validate the in-house code named Flowtran. The trend prediction was in good agreement, but the calculated flow rate was somewhat lower than the experiment. Because of a complicated condition and environment, it was not easy to evaluate the reason for this. And we were working on Stella 2, which is more dedicated facility for natural circulation. So we didn't go into further with this. Okay, next slide, please. Now it's the main of the main dish. Thank you. In fact, the name of Stella is for this activity and facility. I should say Stella 1 is a prequel of the Stella. As I mentioned before, it is aimed for comprehensive review and so that the safety analysis code can be validated. Distinctive feature of this facility is that it is almost like a reactor. So it can simulate the transient responses. Also, the dynamic behaviors can be observed for off-normal conditions. But it is not a reactor with a nuclear fuel, so the power level is at decay heat level. Next slide, please. When we were thinking about the concept of the experiment, we started with identifying what will be tested. So the very first step was to look over the safety event categorization of the reference reactor. From there, we were able to determine the scope of test, which includes most of the DBAs plus total loss of DHRS. Next slide, please. Then we started designing with considerable discussion. The reduced height scaling was decided. In this slide, you can find some basic information and comparison of different scaling methodologies. The key factor was the cost, and to minimize this, the power level and physical space were mainly considered. In conclusion, the 3-level scaling law was selected, and it is suitable for natural circulation phenomena that Stella 2 will be looking at. Before I move on, just one thing to note is that in reduced height scale, the time and velocity scale is not 1-to-1. As you can see on the right bottom side with the red dotted box. Okay, next slide, please. So here's simplified version of how we scale. First, we do the global scaling, that it considers geometry, time, and other thermohydraulic parameters. And second is the inventory scaling, where mass and energy inventory is evaluated. Lastly, Local phenomena scaling is done to assure the proper heat transfer, flow, and energy mixing, heat loss, and so on. On the right top side, the 6 important non-dimensional numbers are shown. Next slide, please. The result of scaling is the requirement for the facility. Considering the most important factor of cost, the height scale was decided to be 1/5, 1:5, and eventually the volume scale is 1:125. The sodium will be used as same as reactor, and pressure and temperature condition will be kept same. General arrangement of reactor internals and components were kept same. The facility simulates the decay heat generation. It simulates primary heat transfer system pump coast down. It simulates pump pipe break event, and it simulates reactor vessel cooling system heat removal. Next slide, please. So what to be seen? The focus of this facility is as written in this slide. The short and long-term cooling capability will be examined. And also, asymmetric decay heat removal operation will be tested. Flow and heat transfer characteristic will be seen. And also, flow distribution and mixing in pool will be seen. Next slide, please. Okay, here are some main design feature of the facility. It has one vessel, 8 loops, and 5 different types of heat exchangers. The vessel size is about 2.2 meter in diameter and 3.7 meter in height. Sodium amount is about 15 tons, and the core power is about 500 kilowatts. Comparably, total system power is about 3 megawatts. And you can see the layouts spinning around on the right side. Next slide, please. Stella 2 resembles the reactor, but there are 3 differences. Can you just click it 3 times to show the red circles? Thank you. Yeah, thank you. Core, of course, is replaced by electric heater. And another difference is that steam generator is replaced by sodium to air heat exchanger. And lastly, the mechanical pump is replaced by pump simulation loop. Let me go into one by one. Next slide, please. So let me start with the core first. It is obvious using electric heater instead of actual reactive nuclear material. Instead of just block heater, which also works, we designed to have same geometry. There is rods, wire wraps, and hexagonal assembly with wrapping duct. And each assembly has one dummy rod for instrumentation at the center. So it is quite complex system rather than just heater. So many details are in this slide. Next slide, please. Designing the primary side is the most important part. Vessel, redan, separation plate, reactor head, inlet plenum for the core, pump pipe, upper internal structure, and etc. To keep the similarity, the inventory was conserved, and the relative elevation of components was also conserved. And we did the design. Next slide, please. The replacement of mechanical pump was suggested to measure the primary side flow rate. So we have taken out the loop and installed flow meter with electromagnetic pumps outside. With this feature, we can exactly measure the primary flow rate, whether it's a forced flow or natural circulation flow. This loop simulates the coast down curve of the mechanical pump by controlling the power of electromagnetic pump. And to keep the similarity, the pressure drop, of course, was conserved. And at the same time, the inlet and outlet position of the pump was conserved. Next slide, please. And sodium loop design. Intermediate and decay heat removal loops were designed to conserve the relative elevation of the heat exchangers. This is very important because the loop is working with natural circulation. Also, the sodium inventory was conserved inside the loop. Next slide, please. Finally, the art of designing lies on here for the 5 different types of heat exchangers: IHX, DHX, AHX, FHX, UHX were designed to keep the similarity. Basically, the conserved parameters are total heat transfer coefficient and the temperature difference. Next slide, please. And of course, before the construction, there should be evaluation. Using 1D system code, as you may all know, Mars LMR, we conducted scoping analysis to compare the transient between reactor and Stella 2. And also, as you can see here, we did a lot of CFD analysis to verify the design. Especially for the core inlet orifice design, we did water mock-up test. Next slide, please. And these are what Stella 2 makes special and unique. It is capable of simulating the pipe break inside the pool and simulating the X vessel cooling. To do this, we have installed specially designed 3-way valve, which has a universal joint long reach arm and very short actuation time. And we have reactor vessel cooling system with the airflow jacket, and there's a blower outside, and the flow rate is controlled with flow meters. Okay, so next slide, please. So what's going on and what will be done? Next slide, please. Here are some pictures of when we were constructing and installing. We have built a dedicated building for this Stella 2 facility, and you are seeing some of the structures here. Next slide, please. And also these are some of the past pictures. On the left top side, there are electric heaters, cores, and in the middle, that's the redone, IHX, DHX, and so on. And on the right side, it's above the reactor head. And those rusty thing is the IHX. And in the middle, there are FHX, AHX, and also there are cold trap. And at the bottom, there are sodium storage tank and gas supply systems and so on. Next slide, please. So now, it is actively operating to get as many as data possible. The test metrics includes enormous cases, and we are vigorously working on it. So this is what will come out. Next slide, please. With the preliminary experiment data, we try to compare with the calculation results of system code. And this is just an example of loss of flow event with one AHX, one FHX failure. And I said it's preliminary, so the detailed analysis will be done in the future. Next slide, please. So for the future, for now, we are very into the experiment, but at the same time, we are looking for the opportunity in future. Of course, within Gen 4 framework, the benchmark calculation activity has been proposed. And within IAEA framework, we will prepare proposal for CRP, the Coordinate Research Project. But other than this, we are looking for the mutual collaboration with various research groups like Idaho, Argonne, France, Japan, and anywhere else. And of course, the industry is very tempted to what we have. So they are reaching out to contact us. Next slide, please. So it's a summary. Next slide, please. Stella program was launched to support the development of first SFR in Korea. It will serve as a strong supporter of PGSFR licensing in future. It is a basic infrastructure for sodium system. And Stella 1 accomplished its mission successfully. Key components, the heat exchanger, for safety of SFR was tested, and code verification and validation completed to assure the calculation results. And Stella 2 is ready to achieve valuable data, potentially be used for licensing, and various activities and works planned under international collaboration framework. Thank you. Thank you very much for listening, and if you have any question, please feel free to ask. Thank you.
Thank you, Dr. Lee. Well, questions are coming in. We'll just take a quick look at the upcoming webinar presentations on our schedule. In November, geospatial analytics for energy and resilience analysis. Oh. In December, the mechanisms engineering test loop facility at Argonne National Laboratory. And in January, the molten salt reactor taxonomy and fuel cycle performance. So Dr. Lee, how big is your team? How many people do you have working under you or with you?
Well, the people involved in this Stella 2 facility is about 12 to 14. And it's a variety of technicians and researchers and someone in the middle. So it should say 12 colleagues.
And do you sponsor internships? Are you working with your local universities, for people to work on their PhDs, or is this something that?
Yes, we do. We have several undergraduate interns, and we were trying to have some of the postdocs, but we haven't got any postdocs yet. But we are still open to accept all those interns and postdocs and so on.
So if you have any questions for Dr. Lee, please go ahead and type those into the Q&A chat pod. I don't see questions coming in at this point. People do have your email. They can reach out to you, I presume, offline if they have questions that come up. If you
Okay,
have a couple minutes, we'll just hang tight and see if maybe people are having difficulty with the dialog box.
sure. Oh, thank you. Yes, thank you.
Are there measurements inside the AHX?
Yeah,
And
sure,
are
of
these
course.
GFD grade?
D grade. Well, we have measurement. You mean the instrumentations? Yes, of course. We have temperature for the air side and get the exact meaning of CFD grade.
She means, I mean local values.
Local values. Well, yeah, it is. We are measuring the inside, the HX, the sodium side, as well as the air side. Yeah, we measure the temperature and we measure the flow rates. That's what we do in the experiment.
Thank you.
Does that CFD grade means how fine? I mean, the resolution? If it's that what it means, we have well, for Stella 1, we didn't have that much many instrumentation, many TCs in the test section. But for the Stella 2, we have put a lot of instrumentations. For example, we have about more than 3,000 temperature points, and we have about 500 pressure points and several more. So in total, the IO points, we call it, the in and out points, it's about 5,000. That's all dedicated for these measurements.
Thank you. We have a quiet group today. Thank you. Under what conditions the experimental data could be shared with other institutions interested in CFD code validation?
Well, that's a very good question, because me and my manager and boss are just thinking of how we can share this data, because we started to open our data in Gen 4 and IA frameworks, but we cannot go on with this because this international framework is not enough. And if we make a mutual collaborations, there will be some ways we can make a kind of a contract or any projects that so that we can share our data, and maybe we can do some experiments of the request from the other organizations or other institutes. But we're still looking the ways how we can share the data.
Thank you. Can you talk about the design cycle for Stella 2? When did the design process begin, and when did construction begin?
Oh, okay. Think I had a slide for that. When we were, well, I talked about the Stella program, and this Stella whole program was, this whole Stella program was for Stella 2, but we started with Stella 1 because we had no experience with this large facility, and also we needed to test the heat exchanger first with a limited budget. So we went on with Stella 1 first, but as I told you before, Stella program was for Stella 2. So the very beginning of Stella 2 is same as the start of the Stella program. So it's about year 2009. But the design started from then, and we had a lot of repetitions, and we finished the basic design in year 2014. I think I've written that in the slides. And after, I mean, in year 2015, we started the specific design. What it means is that we are thinking of the fabrications and installations and structures and where to build it and the buildings and this kind of things. And we finished the design in year 2019, and we finished the construction in year 2020. So it was early 2020 we finished the construction, and since then we are actively working on it.
Thank you. Certainly, you're welcome to move the slides back too, Dr. Lee, if you know, to emphasize some of your answers.
Okay.
I don't see any more questions coming in. Patricia, did you have any last minute thoughts?
What did you say, Bertha?
So do you have any last minute thoughts that you'd like to share? I don't see any more questions.
Okay, very good. I don't see the questions. No, I don't have anything to say besides, again, to thank Dr. Lee for his time and for his excellent presentation. Again, thank you very much, Dr. Lee.
Thank you.
Dr. Lee, where are the publicly available papers on the CFD analysis that you performed?
Oh, well, most of the papers includes the word Stella. So I just suggest you to type Stella, put the keyword Stella, because it must have this term. And regarding the CFD analysis, we have several papers, and I'm preparing the CFD analysis for the heat exchangers. So try to look for it in the internet, and if you cannot do it, just send me email. I'll send it to you.
Thank you. And thanks to the participants who joined with us today and for engaging in enlightening conversation. We appreciate your feedback and your participation. And with that, I think we'll conclude today's presentation. Thank you very much again, Dr. Lee.
Thank you.
Bye-bye.
Bye.
Bye, everyone.